Welcome to part 5 of the video series, Linear Regression, a Linear Algebra Perspective. I wanted to start off by talking about basis vectors. In the previous parts of this series, we had talked of how just two vectors that are linearly independent of each other could be linearly combined to create every vector in a plane. We could then say that those two vectors span this space, which is the plane. Okay. Now, as we had discussed earlier, only two vectors would be enough to span a plane. No more, no less. These would then become the basis vectors of the plane. Therefore, the basis of a subspace is the smallest set of vectors required to span a subspace. Okay. So, for example, let me write this down. Let's say we want to find the basis, one set of basis vectors for R3. Just remember that a subspace could have many sets of basis vectors. So for example, a plane could have many pairs of two vectors that could become the basis. Similarly, let's look at one such set of vectors that could be the basis vectors of R3 or three-dimensional space. And that could be 1, 0, 0, 0, 1, 0, and 0, 0, 1. The next concept I wanted to discuss was the inverse of a matrix. This is an important topic to have a small discussion on because it is involved in the derivation. Okay. So the first point over here is that let's say you have a matrix A. Its inverse would be A inverse written this way. Okay, that's the first thing. Now the second point is this, that A inverse times A is equal to I. Over here, I is the identity matrix. For example, a 2 cross 2 identity matrix would be written in this way. And a 3 cross 3 identity matrix would be written in this way. What you'll notice is that in any identity matrix, you have ones on the diagonals and zeros in every other position. It has to be a square matrix and can be a square matrix of any dimension. Okay. Now let's say over here A is a 2 cross 2 matrix, and therefore even A inverse is a 2 cross 2 matrix. This also means that when A inverse are multiplied, A inverse and A are multiplied, they also give you a 2 cross 2 matrix again. Hence, the identity matrix that's created when A inverse and A are multiplied is a 2 cross 2 identity matrix. Okay. Also, A times A inverse gives the identity matrix 2. Now, number 3 is that not every matrix has an inverse. This is a very interesting point. It says that for a matrix to have an inverse, there are two necessary conditions. Number 1, it should be a square matrix. Number 2, the column vectors should be independent, linearly independent. There are other ways of defining it using the determinant, etc., but we'll stick to this definition. Okay. Now, the next thing that we're going to talk about, the fourth point about A inverse is this. Let's say you have an equation A times X equals B. Now, multiply A inverse on both sides such that A inverse AX is equal to A inverse B. We know that A inverse A gives us I, which is the identity matrix. So therefore, it becomes Ix is equal to A inverse B. Now, I times any matrix is that matrix itself, because if you see, I kind of acts like 1 in multiplication. Yeah. This means that X is equal to A inverse B. A inverse can be found using methods like the Gauss-Jordan method. However, we won't be discussing that today. We'll stick to our main aim for the video. We have finally reached our main aim for today's video, and that is to find the projection vector P of this vector B on a plane. Here too, B is an m-dimensional vector. This means that this is how it could be written: B1, B2, so on up till Bm. This time, if a light source were perpendicularly above B, something like this, a shadow would get formed on this plane, something like this. Like in the previous video, this time too, we need a sort of a definition for this plane like we had for the line, so that we can find this shadow's vector. Therefore, let's say that A1 and A2 are a set of basis vectors for this plane. Okay. Now they would both also be m-dimensional vectors but spanning a plane, which is this plane drawn over here. Therefore, A1 is equal to A11, A12, so on up till A1m. And A2 is equal to A21, A22, so on up till A2m. Therefore, we can say that some linear combination of A1 and A2 will also give us the shadow of B on the plane. Therefore, let's define the shadow this way. Let's say that A1x1 plus A2x2 is equal to P, or the shadow of the vector B, or the projection of vector B. Wherein this x1 over here and x2 are some scalar values, which is what we need to find out. We need to find these values. Okay. Now this can be rewritten in this way. Let's rewrite this equation. We say A1, A2 create a matrix times x1, x2 as a vector, as a 2 cross 1 vector, is equal to P, or the projection matrix. And if we rewrite this, we can say that A times x cap. So we are representing the A vectors as this matrix A, and the x values or the scalar values as the vector x cap. And that is equal to P. This way, every component of A1 is multiplied by x1 and every component of A2 is multiplied by x2. Now we again come to the error. This perpendicular line between B's projection and B is the error, as we had seen even in the last video. So, E is equal to B minus P, which is equal to B minus A x cap. Now, E is also an m cross 1 vector, and the RHS results in an m cross 1 vector. Because B minus AX cap, if you have a look at it, AX cap would be an m cross 1 vector because A is m cross 2 and X is 2 cross 1, so you get m cross 1, and B itself is an m cross 1 vector. And therefore, these two entities or terms can be subtracted. As a reminder, our main aim is to find X cap, which represents two scalars and therefore is a 2 cross 1 vector. And additionally, to find the values of two variables, we'll need two equations. Yeah. Now, we say that A transpose E is equal to 0. Because we want to use both a1 and a2 so that we can find out x1 and x2. Expanding it, just for your information, it would be a1 transpose e, a2 transpose e is equal to 0, 0. But we will use the non-matrix format, this non-expanded format. Now, taking A transpose E is equal to 0, we can rewrite it in this way by substituting the earlier value we found for E, that A transpose B minus AX cap is equal to 0, right? Therefore, A transpose B minus A transpose AX cap is equal to 0. And therefore, A transpose A X cap is equal to A transpose B. Yeah, very similar to what we had seen last time. Very similar. The only difference is this, that this time you cannot divide both sides by A transpose A. Why? Because A transpose A is a matrix and not a scalar value. However, A transpose A is a square matrix and has independent columns because A A has independent columns itself. Okay, so therefore A transpose A would also have independent columns. And hence, you can get the inverse because it satisfies both those conditions we had talked about earlier. Therefore, on both sides, multiply A transpose A, the whole inverse. Okay, in this way. Now, if you notice over here in the left hand side, you can change these values to I. So Ix cap, which is equal to X cap, is equal to A transpose A, the whole inverse, A transpose B. And there we have found X cap. X cap itself is a 2 cross 1 matrix. And on the right hand side too, you'll get a 2 cross 1 matrix. Okay. And therefore, P is equal to AX cap, right? You have X cap with you. You already have A with you defined. Those two vectors are defined. So you can easily find this projection vector P. Now, there's an interesting thing to this, that the same formula wherein X cap is equal to A transpose A, the whole inverse, A transpose B, can be used to even find out the projection of a vector in any subspace in Rm space. So in this m-dimensional space, you take any subspace and you'll yet be able to find the projection of the vector B. The only difference would be that A would be equal to A1, A2, so on up till AD, wherein we could say that D is the number of dimensions in this subspace, and therefore you have D basis vectors, right? Similarly, you can say that X cap is equal to X1, X2, so on till XD, because we need a linear combination with all the D vectors. Therefore, we need D scalars too to create that linear combination. And that's it. That's it for today's video. In the next video, we'll finally start deriving the regression line. So see you then, and I hope you have a great week ahead. Bye-bye.